The next speaker who needs to set up a machine here, so I'll do a little cover-up, is Bernhard Schölkopf from the Max Planck Institute. And we're going to switch gears a little bit, and he's going to talk about how the use of causal models can improve a variety of machine learning tasks, such as domain adaptation, semi-supervised learning, and the like. So, Bernhard?
Thank you very much. And thank you very much also for the opportunity to help organize this symposium here and speak here. So the title of my talk is Toward Causal Machine Learning. So I'm going to start with an example from machine learning, which has been my field of research for most of my career. So we try to get computers to perform learning and inference. This has many applications. Here's an application from a shopping website. So if you go to this shopping site and you look for something called a glass circular cutter, it's a device like this, you attach it to glass and you can cut a hole into glass. Then using past purchases of other customers, we can learn that people buying these items like to buy some other things to go with it. And we can make recommendations. Such as this. So this is a real example. So this is a balaclava. This is a baseball bat, brand name Hooligan, and this is a rucksack with bat wings. I'm not going to explain all of them. So many of us deal with data as scientists, and drawing conclusions from data is something we think we're good at. So let's assume we've measured two observables, and we find the points to lie approximately on a straight line. We might be willing to infer a corresponding law of nature, but already Leibniz pointed out that even if we scatter spots of ink randomly on a piece of paper, for instance by shaking a quill pen, we can also find a mathematical equation satisfied by these points. So Leibniz argued that we wouldn't call this a law of nature, because no matter how the points are distributed, there always exists such an equation. So according to Leibniz, the equation somehow needs to be simple. And of course, this begs the question, what makes an equation simple? And a number of people have thought about this. And I will only mention, for instance, the mathematicians Hermann Weyl, Gregory Chaitin. The physicist Rutherford took a pragmatic view. He said that if there's a law, it should be evident from the data. So if your experiment needs statistics or inference, you ought to have done a better experiment. So I'll try to convince you that there are interesting inference problems that are non-trivial, so problems where better experiments may not be enough. So we're currently experiencing a revolution, I think, in the natural sciences where people try to solve exactly those non-trivial inference problems. And it turns out that learning and inference is playing a central role in this. And this is just one simple example of that. It's a problem from bioinformatics. Here the task is to classify human DNA sequence locations into several classes using 15 million training sequences and a so-called multiple kernel, SVM. And I'm not going to go into detail, but the point here is, as we increase the number of training examples, of course, performance increases. At the end, it's quite respectable, 70%, which at that time was the best available performance. But if we have small training sets, let's say we only take a few hundred, then we are essentially at chance level. So this is a kind of problem. If you only have a few hundred observations, which is probably all a human looking at the data would ever consider, you're doing a chance level, but there is a lot of structure in the problem that we can see if we have a lot of data. And this is a good example, I think, of a hard inference problem. And it has some properties that are typical of these problems. It's high dimensional. You have to consider many factors simultaneously. The regularities are complex, for instance, nonlinear. We have little prior knowledge, so we don't have a mechanistic model for the data, and as a consequence, we need big data sets. Now, machine learning methods are used everywhere. They're used in your mobile phone, in your camera, they're used whenever you search the web. Generally, they're used whenever we have lots of data and little knowledge of the underlying mechanisms. We have a pretty good understanding, I think, by now of how machine learning works. Also a good theoretical understanding, provided nobody changes the underlying system. Unfortunately, that's often unrealistic, and then things break. It has been mentioned already several times today, so I'm going to hammer this a bit more. So let's illustrate this with another shopping example. So in this case, the customer is looking for a laptop rucksack, and the shopping website recommends that he should buy a laptop to go along with it. But this somehow feels wrong. And intuitively, we would say that buying the laptop is a cause for buying the rucksack, whatever that means, and buying the rucksack is some kind of effect. We want the rucksack because we want to put our laptop into it. Now, both of these things contain information about the other one. So the cause contains information about the effect because it controls the effect or it has the influence on the effect, and the effect because it carries a footprint of the cause. Now, if we look at this in terms of information theory or statistics, the mutual information between these two things is symmetric, so it's going to be the same. It doesn't matter what's the first, what's second. And if we only look at that, there's no directionality. This directionality that we intuitively think is there gets lost. Another example to illustrate the difference between dependence and causation, and I think you've all heard this example, is about the storks. There's a strong correlation between the number of storks living in a country and the human birth rate. So this is the data. There's a nice paper about this. But of course, nobody would try to increase the birth rate by increasing the number of storks. So the statistical model doesn't make predictions for this. So in summary, it seems like causal links create dependence, but vice versa, it's more complicated. This guy here, Hans Reichenbach, had a profound insight into the link between causality and statistics. So this was a very interesting person, actually. And the insight goes as follows. He formulated the common cause principle in a book which is called The Direction of Time, linking causality and probability. And this principle postulates that if two observables are statistically dependent, then there must be a third one called Z, which causally influences both of them. So this is now a causal diagram. The arrows mean causation, where this third one might coincide with X or Y. So direct causal links are special cases, but sort of the generic case would be this one. And he postulated, moreover, that this third quantity screens X and Y from each other in the sense that given this third quantity, X and Y have become independent. Their share comes from Z. So this is nice and somehow still at the heart of causal inference methods. Now I'm going to describe a model. You already heard about it before, several talks of causality, which actually can be shown to satisfy the Reichenbach principle. So it's this functional causal model or structural equational model point of view. In this model, we assume that we have a set of observables that are connected by arrows representing direct causal links. Each observable is determined by its parents in the graph, these red things, so this is our observable, and by an unexplained variable ui, which is not shown here in the picture. Sometimes this is called noise or unexplained for u. The noises are random variables, which implies that everything else becomes random as well, and we get a joint probability distribution. We're assuming that these noises are jointly independent. So I'm going to deal with the simplest case. It turns out that this joint distribution over the observed variables, the xi, has a particular structure. It has particular conditional independencies, which are specified by the so-called causal Markov condition. So from the graph structure, together with the independence of the noise variables, we get the implication that there are certain conditional independence properties. As an aside, I should say also that this kind of model leads to a graphical model, and every graphical model with respect to a DAG can be written this way, but not uniquely. So a functional causal model contains more information than the graphical model, and specifically it also allows us to predict the effective interventions, and it lets us make statements about so-called counterfactuals, but that's an aside. So the central question of causal inference, or maybe I should say of causal structure inference, is the following. Suppose we observe a lot of data, actually so much data, that we can estimate the distribution P that generates our random variables, or the distribution of our random variables that generates our observations. Given sort of this infinite amount of observations, can we recover the graph from this? In other words, can we infer the causal links in this graph from purely observational data? There's a beautiful, but not yet complete, or maybe not definitive answer that people have worked out. And this answer says, I told you before about this Markov condition. We have certain conditional independence property. So the answer says, let's do conditional independence testing to find out as much as possible about the graph that might have generated the data. It turns out this doesn't give us a unique graph. It gives us a class of graphs that contains the correct graph. That's beautiful, but one could argue that there are still some problems with this. First problem is, has been mentioned already a few times today. It's called faithfulness. The Markov condition that I told you about on the last slides actually makes a statement about implication from graph structure to conditional independencies according to the distribution. Now, if we want to infer from data to graph structure, we have to go the other way around. So we actually need an implication in this direction, and it has been argued, and this is called faithfulness, that it's extremely unlikely that there are graphs that there are distributions that mislead us about the structure of the graph. But then others, including people sitting in this room here, have argued that actually in the case of finite data, this is hard to really justify. A second problem that maybe is obvious to someone who comes from machine learning or statistics is that if the functions sitting on these nodes, so I told you at each node we have, or maybe I didn't tell you, I should have told you, so each variable is a function of its parents and an independent noise. It could be a different function everywhere. These functions could be very complex. Now, if these functions are complex, then conditional independence testing, which is something we have to do to solve this problem, based on finite samples, becomes arbitrarily hard. So we can't really assume that this can be done because it's really arbitrarily difficult. Final problem, which is the one I will be talking about mostly, is that if we have only two variables in the graph, so sort of should be in some sense the simplest case, there are no conditional independences because they always involve three variables. So there's nothing we can do for stuffed. So two variables. This problem, of course, has been studied before, for instance, by philosophers. So this guy, Nietzsche, writes about it at the beginning of this book here, and he calls it the error of mistaking cause for consequence, or reason's intrinsic form of corruption. So I want to talk about two ideas how to deal with the two-variable problem or the cause-effect problem. First one is something we refer to as independence of cause and mechanism. So I should say in the two-variable case, our complicated graph from before, this thing reduces to something like this. So here we have cause and effect. Cause is influenced by a noise variable and nothing else, but actually we can identify it with the noise variable and just think of the cause as a random variable in its own right, or in the first place, and the effect is a function of its parent, the cause, and another noise variable. So that's how the structure looks. And the function together with this noise variable determines the conditional of effect given cause, which we can think of as the mechanism that turns cause into effect. Now we're going to assume that this mechanism and the input distribution, the distribution of the cause, are independent. And I put this in inverted commas because this is a bit of an informal thing. One can formalize it in various ways. I'll show you one way later on, but let's keep it informal for now and rather show you a picture. So this is an object composed of several pieces, which is called a Bochet chair. This is from some art exhibition. And when we see this object here, so this is not part of the object here, our brain makes the assumption, or whenever we see any object, our brain makes the assumption that the object and the mechanism by which its light reaches our brain are independent. So we can violate this assumption, in this case by looking at it from a very specific point, namely through this little hole here. And if we do that, perception goes wrong, and we perceive a 3D structure which in reality isn't there. So then the thing looks like a chair, and that's why it's called a chair. Another nice example of this effect is this painting from the 16th century by Hans Holbein, which has this strange-looking object down here. But as you walk around to the very far side, you can see this scary-looking skull. So the painting is called the Ambassadors. And it's another case where if we look at it with a very strange mechanism, suddenly something surprising happens. So let's postulate that in the generic case, mechanism and input are independent. So here's a little mathematical picture. In the zero, there's no added noise, no additional noise. The simplest possible case, let's assume we have some input distribution. We have a mechanism, so no noise means it's just a deterministic function. This function turns the input distribution into an output distribution. And if the function is non-trivial, in other words, non-linear, then this output distribution contains a footprint of the function, because wherever the function was flat, the output density takes larger values here. So if this is independent of this thing, then, roughly speaking, this thing here won't be independent. And this can be formalized, but I don't think I should go into details here. So we can define certain random variables. We actually view the density of the input as a random variable in the log of the derivative of the function. We postulate that the covariance between these random variables vanishes, and then we can prove that unless the function is the identity, that in the backward direction, this equality here is strictly violated. So this covariance will be strictly positive. And this can be analyzed in different ways, for instance, using information geometry, and can be interpreted as an orthogonality in information space. And roughly speaking, one interpretation is that the irregularity of the output distribution is a sum of two terms. One is the irregularity of the input distribution, and the other one is the irregularity introduced by the function. So that's what the function would generate if you were to feed it with a uniform input. And it turns out this is additive in the forward direction under our assumption of independence, but this additivity will be violated in the backward direction. Okay, so that's the first idea. The second idea, how to handle this cause-effect problem, is to restrict the functional model. So I told you before that from a priori there are no restrictions on which functions we put on the nodes in this graph, which seems, from a machine learning point of view, quite scary, because normally if we have no restrictions on the functions we learn, then we can't do anything. So let's think about this for the two-variable case for a second. So this is our general functional model. Now think of the noise as a discrete variable, make it simpler, taking d different values. Then with this kind of model, so it's a function of x and the noise, we could, for instance, implement a system that randomly switches between d different mechanisms, converting input into output. So that's a very rich class of models, and in fact, nothing restricts us to d values. It could be a large number, or it could be even continuous. So we could, without restrictions on the functions, we could really make this very complex, and intuitively it seems like there should be no hope of identifying this kind of model from data. So one way to make it simpler is to think of like a first-order expansion in terms of the noise and consider the noise as additive. If we do this, then it turns out we can prove identifiability. So we can prove that if the data has been generated by such a model, then typically we won't be able to fit such a model in the backward direction. So there's only one direction in which such a model exists, up to some very sort of degenerate cases down here. And the intuition is simple. Think of a nonlinear function and add some noise, and actually for the sake of the picture, let's assume the noise has bounded variance. Then the noise will have the same variance everywhere here. Remember that x is independent of u, but then in the backward direction you won't be able to have the same noise everywhere. So in the backward direction the noise would be dependent. Okay, so this is nice, this kind of asymmetry. It has been generalized in various ways that I'm not going to go into detail on. It has been generalized, for instance, to graphs with more than two vertices. We have some initial results also for confounders with additive noise, but let me rather move on to very briefly talk about something that's hopefully new to everybody. I also wanted to include something for the experts here, and which makes another link which makes a link to the field of machine learning where I grew up, kernel methods. So this is using kernel maps of functional causal models, and I'll briefly tell you something about this in the next 5 minutes, including some background on kernels. So here, again, structural equation model, independent noises. Now note, and this is with respect to a directed acyclic graph. So what we can do is we can always substitute the equations for the parents in here. And if we keep doing this, then at the end, each variable is a function of only noise terms and all independent noise terms. So in the end, for each xi, we get an equation like this. And we have a nice way of, so this is now a function of independent random variables. And we have recently developed a nice way to compute such functions using kernel embeddings. And then it turns out one can use these kernel embeddings to devise yet another method for the cause-effect problem that I briefly mentioned. Now, a kernel, positive definite kernel, is such an object that takes two inputs from some domain. It's a symmetric function, and it's a function such that whenever we compute a whole matrix by taking a set of points as inputs, this matrix is positive definite. In all applications of machine learning, certain issues need to be addressed one way or another, and kernels provide a nice unified framework for this. And three such general problems, I think, are we need a notion of similarity, and the kernel can be thought of as such a notion of similarity. The kernel also induces a representation of the data, and in this case, it's a very nice representation. It's a linear representation in a dot product space, even if the original data were not vectorial to begin with. And the kernel also encodes the function class used for learning. So if we take a smooth kernel, then it turns out the functions that we can construct using learning algorithms with this kernel are also smooth. And the best known kernel method is support vector machines. So when they were developed, the central idea was that each observation is mapped into a so-called feature space or reproducing kernel Hilbert space. And in that space, we then use a linear method to classify the data. But since this mapping is not linear, we can end up with nonlinear decision boundaries in the input space. And depending on how nonlinear this mapping is or how nonlinear the kernel is which generates that mapping, these corresponding surfaces corresponding to this hyperplane in high-dimensional space can be rather complex in the input space. So this is based on mapping individual points into such a feature space, but now we understand that we can also map sets of points into feature spaces, and we can even map continuous probability distributions into feature spaces. So that's quite nice. So here we have sets of points. That's the definition. So if phi is the mapping that we use for individual points, we just take the mean over these phi's for all points. In the case of a distribution, we take the expectation. This is nice, and by the choice of a kernel, we determine which information we retain when we map into this linear space. So with a very simple kernel, we might only retain the mean or the expectation. With a polynomial kernel, we retain moments up to a certain order. And if we have sufficiently nonlinear or rich kernel, it turns out we don't lose any information. So we can work with these distributions as elements of this Hilbert space, of this linear space. And that's, of course, extremely useful for theory and for developing algorithms. So this led to a set of methods to deal with higher order structure or higher order moments in distributions. And some of these methods are quite useful actually for causality research. In particular, independence testing and conditional independence testing. So I'm not going to talk about this in detail. And also a new method to compute functions of random variables, functions of independent random variables by kernel mean embedding and sort of lifting these functions from functions on individual samples or individual points to functions on random variables. And so we're going to apply this for the cause-effect problem. So we take, again, a two-variable graph, and we assume additive noise again. And then what we're going to do is, so we have if additive noise holds true, we have this equality here, which means that also when we map these points into the feature space, they will map to the same point, this quantity and this quantity, so this distance here should be 0. We can write down an estimator for this distance, and this way we can construct estimators both for the direction x to y and for the direction y to x. So in the correct causal direction, this should be 0 in the backward direction. That's the question, and it turns out when one can prove if the additive noise model is identifiable, so if it's in principle possible to tell, or if it's in principle possible to tell which direction admits an additive noise model and which doesn't, and if the kernel is characteristic, so sufficiently nonlinear such that we don't lose information, then the forward estimator converges to 0 in probability, and the backward estimator converges to a value non-zero. So that's I haven't included any empirical results, but this method, it turns out, also works. But I'll show you empirical results now for the other methods, using a set of cause-effect pairs that we have gathered over the years, for which we think there's a reasonable ground truth, even though one can argue about this in some of these cases. And the bottom line is that we find that our methods, maybe I'll briefly stop this, our methods, which are the ones shown in red and blue, can recognize cause and effect better than chance. So the gray area is what you would expect if your method were random guessing. So in 95% of the cases, you should be in this area. If you find that a curve is consistently outside, that's promising. We also have applied these methods to detect whether a time series runs forward or backward. This also works, and recently we applied it together with some colleagues from computer vision to videos. So this video here in the background, we didn't apply to this one, but that's a nice example because it's illustration of this problem, and it's actually a case where the direction is easy to detect for us. This video was shot by the Lumiere brothers in 1896, and it might well be the first case where people could see time go backwards, because the operator of the projector actually at some point started turning the handle backwards, and then you could see these guys doing everything backwards in this wall coming up again. Wait until the wall comes up again. Okay. So where do we stand regarding what I referred to as the central problem before? So can we recover the graph from the distribution, or how can we recover the graph from the distribution? So I told you before that the existing methods that do conditional independence testing, they exploit the fact that we feed in independent noises at each node. And these noises then sort of spread through the graph and pick up a footprint of the topology of this graph, which can be picked up by asking conditional questions of the form of what does this node know about this one that this one doesn't know, etc. So I think it's sort of intuitively clear that you get this kind of information if you start with independent noises, and that's a powerful method. The new methods that I told you about, they sound different, but actually they are somewhat related, especially the first one, so independence of cause and mechanism. You can also think as a form of independence. So it's not an independence between different noise terms, but the independence between a noise and functions. And again, if you think of this noise spreading through the graph, you can just imagine that if you have non-trivial functions sitting on these nodes, then the noises as they pass through these nodes pick up signatures of these functions. So in principle, there is information that comes from these functions, which somehow is hard to capture in statistics, but the information in some other sense is there, and I hope I convinced you of this. Second case was we can restrict function classes. We can, for instance, postulate additive noise, in which case simply this kind of model, the class of distribution that can be explained with such models shrinks, and therefore inference becomes easier. One can also think about, and this is probably still an open question, how to combine all these aspects. We try to do this in an approach that uses Kolmogorov complexity instead of Shannon information, which I think is quite interesting. I'm not saying that it's practical, but I have one brief slide about this, and interesting thing is that so you also start with the structure equation model, but actually it's not equations. There aren't equations anyway, there are assignments, these structure equations. But in this case, we have computer programs running on some Turing machine. We have some inputs. These programs produce outputs, which then get fed to the next node that uses them as inputs, etc. And you can generalize all these notions of independence, etc., of course, to Kolmogorov complexity or algorithmic information. And in the end, if you use these terms, you can essentially formulate like a theory of graphical models that starts with this kind of functional model. And then you also get a Markov condition where you don't have Shannon entropy but Kolmogorov complexity, and you get a decomposition of this graphical model, not in terms of these conditionals, but you get an additive decomposition in terms of Kolmogorov complexities of conditionals, etc., or of conditional Kolmogorov complexities, and so on. And this is, of course, something that in principle can be done also for individual objects. And it's also interesting that it sort of treats noises and programs the same way. So there's no distinction between the functions and the noises anymore. Okay, so finally, applications. How can causal knowledge help machine learning? I have two brief applications. The first one is semi-supervised learning and domain adaptation. In this case, we want to exploit knowledge about what's cause and what is effect. And briefly, it turns out that if we have simple cause-effect structures, then it makes a difference whether our direction of prediction, so in machine learning we take an input, predict an output, whether this direction is aligned with the causal direction or whether it's going in the opposite direction, in which case we would call it anti-causal. So many problems in machine learning are anti-causal, but some of them are causal. And it turns out that if we think about what effect this has, then the answer is non-trivial. So if we want to do a machine learning problem, we always want to estimate properties of a conditional distribution for y given x. Now let's make our causal assumption that the distribution of the cause and the mechanism are independent. Now in semi-supervised learning, we want to improve the estimate of p of y given x by additional data from p of x. Now unfortunately, if we do this in the causal direction, we just assume that these two things are independent. So no matter what additional things we might learn about this, it doesn't help us predicting this. In the anti-causal direction, it does help us. It's the other way around if we think about covariate shift. Covariate shift, we're considering the situation where p of x changes between training and test. If that is the case, then if it's the case in the causal direction, then by our causal assumption, these two things are independent. So we would not expect that this mechanism here is affected at all by a change in this quantity here. So we would expect that this should be the easy case, whereas in the opposite direction, it is affected and it's more complicated, although it's still interesting to think about how one should take this into account if one knows that the causal structure is like this. I think Peter Mühlmann will talk about something related, and it's going to be interesting, I think, later this afternoon. Empirically, now, people have found that semi-supervised learning sometimes worked and sometimes didn't work. Without having really a full understanding what characterized these two classes of problems. And now we have a hypothesis, and we didn't run our own experiments, but we did a meta-analysis of other results, or benchmark studies people had done, and it nicely confirmed our prediction. So we found that semi-supervised learning very nicely failed in all cases where we thought, by categorizing things beforehand, that the underlying prediction problem was causal. And semi-supervised learning worked in many, but not all cases where the problem was anti-causal or confounded. So this is nicely consistent with the hypothesis. And also some support for the hypothesis comes from the fact that all the previous attempts to motivate semi-supervised learning actually can be linked to our causal assumption. But maybe so people know, for instance, the cluster assumption says that points in the same cluster of the input density should have the same label. So the boundaries, decision boundaries should lie between clusters. And of course, if you just read this, you see this is talking about a link between p of x and p of y given x. And the same holds true for these other assumptions here. Okay, so last application is from astronomy. We are looking at the data from the Kepler telescope. In 2009, there was a space telescope was launched, the Kepler telescope. to observe a tiny fraction of our Milky Way. So this is our sun. We're looking in this direction. There's quite a few stars here. We have the same distance from the center of the Milky Way, etc. Various reasons why we look at this area. This telescope, or spacecraft, is named after the astronomer Kepler, and it has been staring at the same patch of sky, roughly here next to the constellation Cygnus, for more than 4 years, until eventually it failed, and now it's another story. It's more complicated. But in this patch here, it observed the brightness of 150,000 stars. And it took a picture like this one here every half hour. Each picture has an exposure time of half an hour, and then there's the next picture. Now, Kepler tries to detect exoplanets that pass in front of their host stars. This leads, if such a planet passes in front of the star, we get a slight dip of the light curve. Now, this is a very faint signal. If we think about how strong the signal would be for our own star or for our own planet, so if we go somewhere out in space and look at our solar system, first of all, we have to be lucky and be in the right direction. With a uniform distribution over the sphere, we would have a 0.5% chance to be lucky and see Earth transits in front of our sun. And then if we did, we would see a signal of 84 parts per million that lasts roughly half a day. Now that's not a large signal, especially if you think about all the noise sources. So that's why people try to do this with a telescope in space, because with ground-based observations, the noises would be significantly larger than this. But even with a space telescope, it's a difficult problem. So this is on the Kepler CCD, each star is made up of a number of pixels. And if you look at these pixels, they all belong to the same star, but they don't all look the same. Now the scaling is very much blown up here, so in reality they would look more similar. But if you zoom in, you can see these differences. Stars would be reasonably stable, but if you exaggerate the differences, you see they are different. And you can see that we have a problem here. So the problem, the astronomers they have developed a data processing pipeline that tries to remove all the systematic errors that cause these differences. And they've developed this method. It's called pre-search data conditioning. And they derive these light curves that are called PDC flux curves. So this is such a curve, and here you can see a little exoplanet transit. This is an easy one, quite pronounced, but of course we're also looking for harder ones. Now we built a causal model that tries to improve upon this pipeline. In the simplest case, the model assumes that our measurement of interest is this star here. So that's, for instance, one of the pixels contributing to such a star is a sum of the underlying star. So that's the true thing out there in space, and a noise source. So this sort of are all the systematic errors that the system makes. Temperature fluctuations, pointing errors, etc. Now it's difficult to reconstruct Q because we don't know these noise sources. But what we do know is that these noise sources also affect other pixels. And we're observing 150,000 stars. So we have a lot of other stars here. So we assume that this also affects the other stars, and we're assuming, moreover, it affects the other stars in this simplest result. We have some generalizations of this. It affects the other stars in a way such that, in principle, from these other stars, we could predict the effect of the noise completely. So more completely, I should say, we're assuming that our signal is a sum of this true signal and the noise, and a function of the noise. And we're assuming that this function of the noise can, in principle, be predicted from these other pixels, although we don't assume that we have knowledge of this function psi here. So if these assumptions hold true, then it turns out, and this was surprising to me at the beginning, although it's not difficult to prove, that we can perfectly reconstruct this unknown signal Q up to its expectation. So we can fully reconstruct this random variable by subtracting the conditional expectation of y given x, so just the regression from this observed random variable y. So up to a constant offset, we can reconstruct this Q. So here we have the curves again. Let me zoom in. So I should say this is done together with astronomers at NYU. This is the PDC curve that the astronomers are using. This is for the same star an example of our normalized version, and then of course the hope is that this exoplanet should somehow become easier to detect in this normalized one. So you certainly see that it's a cleaner light curve. This is promising, and in fact this process of trying to find new planets is underway, and we recently compiled a list, or I should say the astronomers compiled with our help a list of exoplanets candidates for data from Kepler, actually for data that looks more messy than this, because it's data from the sort of so-called Kepler-2 campaign. Something broke in the satellite, and now it's producing worse data, but of new stars that haven't been analyzed yet. And we think we are good with bad data, so we looked at this immediately. We produced a list of candidates, and it looks like quite a few of them are actually real, so some of them have been confirmed already. So I have to gradually get to my conclusions. I know this thing is quite generous, because my laptop says I'm at 40 minutes, but it's still yellow. It's nice, I appreciate it. So just to conclude, I'm with an attempt of some kind of taxonomy. So I was originally trained as a physicist, and physics is the world of mechanistic models inferred by smart scientists, so somewhere up here. Then I moved all the way to the other extreme, down here, statistical models, machine learning models. Of course, I never regretted this, but in recent years, I got quite interested in what's in between. And I think causality is a field that's somehow in between these two extremes. So it allows us to predict things that machine learning can't. So if you have a mechanistic model, you can do everything, but with machine learning, you can only really predict in an IID setting with the standard methods. Causality allows you to do some things, predict under changing distributions, interventions, counterfactuals, etc., that you can't do with machine learning. And I think also thinking about a problem causally informs how to do machine learning on difficult tasks. It tells you something about things like semi-supervised learning. Maybe it gives you some insight how you should be modeling systematic errors, etc. And I think we've only, at least for myself, speaking about myself, we've only scratched the surface in that so far. So I think this is exciting, and it's interesting to think in this spectrum, and it's interesting to try to connect these different fields. And we're trying to do this. For instance, we've worked also on the problem of given a set of coupled differential equations, so a really physical model in time. I mean, time is something that hasn't been mentioned so far. So we feel it has something to do with causality. So taking a physical model in time, differential equations, how to derive a structural equation model from this. And there are lots of other interesting problems here, and I think with that I should conclude and thank all my co-workers. Thank you very much.
Could you just say a few words? Your pairwise procedure, could you say what happens if there are confounders? I mean, if you're not trying to decide between A goes to B or B goes to A, but A goes to B versus some hidden variable between the two.
If there's the possibility, so we have a method that allows for the possibility of a confounder. In this case, the assumption is that both X and Y are have additive, are confounders plus additive, you have a confounder, you take a function of that confounder plus independent additive noise, and so each of the two observed variables is a function of the confounder plus additive independent noise, and you can try to reconstruct, given observations of X and Y, your joint distribution like that. And in principle, the identifiability results are weaker than in the case where we don't have confounders, but in principle, in the limit of small noise, this becomes something like a deconvolution problem, and in principle it's solvable, and it should, if all the assumptions are correct, the small noise is small enough, etc., it should give you a result of the form either there's a confounder with additive noise, or X causes Y or Y causes X. So the results are weaker, but in principle, one can also use this additive noise trick to make such a situation identifiable.
So another method that you didn't have time to mention for learning causal graphical models is a Bayesian method. And my question is, to what extent can you frame the functional approach that you discussed in terms of a Bayesian approach? Is it subsumed by a Bayesian approach to causal discovery?
So I haven't been able to do that. I had a number of discussions with people. I've had this reaction before, and I've sat together with people who consider themselves Bayesian and who said, well, this looks like it should be easy to interpret it as a Bayesian way, and we didn't directly work out how to do it. But I think it would be an interesting problem, and probably it's doable, at least in some of these cases. I mean, I think, for instance, the case of independence of cause and mechanism, I imagine is a little tricky. I wouldn't see directly how to do that, but maybe it's possible, yeah.